So this one's going to just be a coverage of what is radiation. Now this is a rather important one because of the historical legacy with radiation. There is a very large social misunderstanding. Basically, go back to the before the Cold War, World War II, when we were first developing the first radioactive materials to make the bombs. We had a severe lack of understanding of what it could do. We didn't really understand the damage it would do to cells, the half-life of the materials, like how long they would last, the toxic remnants and everything. Like, there is a lot of problems. Well, nobody wanted to really talk about those and stop using them because the Cold War followed World War II and we needed bigger and bigger bombs, and so military kept testing them. The public would get worried and military would say, oh, don't worry, there's not that much radiation. Which was true. The nearby towns in Nevada and everything were not hit by that much radiation from the explosion. But what would happen was the fallout, the toxic elements that would drift on the wind, the continuous radiation exposure over time would do damage, and then people would get sick and cancers and diseases, and they would say, look what so little radiation did. And so people were very afraid of it. And it wasn't also very well understood, which is why, comic books and everything, like the superheroes get exposed to radiation and gain mutant powers. Like, that won't happen. As a result, there's just a lot of misunderstanding spread throughout society. Our goal in this section is not to make you nuclear chemists. It's not so that you could calculate how long and how far away you could stand next to a plutonium device or anything like that. All we're looking here is to help you understand what is radiation really, why is it that it can be safe at some times and dangerous at others. It's really about the type and the amount, because you are always bombarded by radiation. From the sun, from the earth, from bananas if you eat them, your own bones. Radiation comes from a lot of sources, and we are always exposed to some. The amount and the type is what makes it dangerous or helpful, and that's what we're going to discuss. And so the goal is that if you had a patient one day, someone you're helping, and they're afraid of an MRI or an X-ray or radiation treatments, what can you relate to them to help them understand why they could indeed ingest that barium dye and not have to worry? Or take that X-ray and it's not significant. That is our goal for here. So to start with, let's talk about what is radiation. At its simplest, radiation is energy over space, over distance. To radiate is to emit energy and send it away. So radiation are just forms of transmitting energy over a distance. There's a couple different types. There is photonic, which is light, and there is nuclear, which is the one we usually think of when we think of radioactive materials. So photons, light, is pure energy. Now, that's one that tends to catch folks a lot, but light, by its very nature, is just pure energy. There's no physical mass to light. So when you turn on a light or source in your home, a light bulb or something, it starts kicking out light. What is actually being sent out to hit your walls and bounce off and then hit your eyes is little packets of energy. What happens is it bounces off a wall, it reaches your eye, and then the energy is absorbed by molecules in our eye to send a signal to our brain. And so we use that little packet of energy to crack a molecule, which causes a protein to change shape and sends the electrical signal to our optic center. And so we actually use that little bit of energy to do something. It is consumed. Most of the time, if you turn light on something, it just kind of heats it up, vibrates it more. And so that's why if you've ever touched a light bulb, it's very hot. Not a smart thing, probably don't do it. I may have done it plenty myself, but I always recommend others not to do foolish things that I've done. So let's talk about light. Help us understand a little bit about it. Most of us think of light as visible light. These are red, blue, green, purple things you can see, stuff your eye picks up. Well, there's a certain amount of energy needed to crack the molecules in our retina that send the signal. And visible light is in that range. It picks up those energies and absorbs them. But if we think about the range of energy possible, there are things that are higher in energy, things like ultraviolet. UV light, well, if you get, normally in the sun and daylight you don't get burned, but if you get a lot of direct sun, the ultraviolet burns your skin. Ultraviolet light is higher in energy. Well, visible light was fairly good at exciting electrons, which is how we can send the electrical signal. Ultraviolet light is good at breaking bonds. If you think back to our electronic orbitals, basically visible light can knock an electron from like a 2s up to a 3p. It can move it, but it stays on the atoms, where ultraviolet is enough energy to just knock it completely off the atoms. So ultraviolet can actually do damage. The molecules that make up your cells, the proteins in your body, the collagen that holds them together, the lipids that are the cell wall, these can get damaged. And so if you've got, if you do biology, you've got a phosphodilipid, so polar bit and two long carbon chains. What can happen is a UV light can come in, it can hit, cause a little break, and what will happen is, there you go, that part will just break free. You can actually damage a molecule. Now you are built out of like 10 to the 27 moles of molecules. Like, losing a molecule means nothing. If you've got dandruff, scratch your head, you just lost tons of molecules. We are built to take some damage. We constantly regenerate. Like if you ever get a sunburn, it hurt for a little while, but your skin just regrew, you shed some peeled skin, and you were better. If you ever got a bruise, like you did some damage, but your body heals it up. We naturally, from scrapes and bumps and things like that, lose some molecules and just rebuild them. And so this doesn't really bother as much as long as it's not too bad. Continuing in this vein, though, above ultraviolet, you eventually can get to X-ray and even gamma ray. So X-rays, they are very high energy. They'll definitely knock electrons off things. But they also pretty good at passing through material because of that high energy. And so if you get an X-ray for, say, a broken arm or something, the X-rays go in, and it mostly passes through the watery parts of your skin and flesh. So most of the X-rays pass through your muscle and your flesh and everything, but if the bones, they're denser, they're made of minerals instead of water. Those are a little bit better at absorbing X-rays. So if few of the X-rays get absorbed by the bones, less of that reaches the film, and so as a result, you can see the difference between where your bones are and where non-bone material is. And so the X-ray can see inside of you, because what really happens is it passes through you, reaches a piece of film, and then interacts with that film. Now, in the early days, we used way too many X-rays. Have you ever seen that kind of cartoon thing where they stand behind the big screen and it shows their bones? That actually existed. They didn't realize that X-rays could be damaging at the time. So if you stood in front of it for too many hours, people got cancers and things like that. That's because they stood in front of it for hours. Modern X-ray machines are so incredibly low power, so few X-rays, because they only need a couple to reach the sensor. I mean, we can have film, which is pretty sensitive, but we also just have digital ones now. You only need to move an electron for our digital sensors to pick it up, which means you need one X-ray. Well, as we kind of saw over here, looking at UV, I mean, sure, you might damage a molecule or two, but that's nothing. Your body can take some damage. So when your X-rays, if you're at the doctor's or the dentist anymore, they don't really do almost any damage. Yes, some molecules do, but we hit so few out of the moles of them in your arm. We're talking about countable numbers of them being damaged versus a mole. It means nothing to your body. And so we can see how many get through, we can see where the bones are, and if you got a crack, some X-rays get through that crack because there wasn't as much material, and you can see the damage. Way up top, gamma rays. Gamma rays really only come from dying stars and black holes. They are insanely powerful. To give a scale here, visible light is in the realm of 10 to the minus 19 calories, where gamma rays are 10 to the minus 11. So they are billion times more energetic each. We can also go down. Under visible light would be things like infrared, so heat. So if you ever have something giving off heat at a distance, that's actually infrared photons. It's a form of light. It's heat vision from movies, Predator, things like that. But the idea is there's just an energy to make a molecule vibrate, and that energy tends to be in the infrared range. And since vibration is so tied to thermal energy, we call it heat energy. This is the microwave region. This is where your cell phones work, your microwaves work. Below that, you get into FM and TV broadcasts, and then eventually, AM radio. So this is kind of the gambit of types of light, right? And then they're just different sources of small amounts of pure energy that shoot out over distance. AM radio is incredibly low amounts of energy. Gamma rays comparatively 1 trillion times more. But AM radios are kind of easy to generate, and it's almost impossible to make gamma rays. So this is the idea of light. It's just a form of radiation that we see and interact with all the time. Most of it is not harmful to us. But we're going to put a dividing line here. Below we have non-ionizing. And above we have ionizing. So, think back over here where we were talking about ultraviolet being able to damage a molecule. Basically, once you reach a certain amount of energy, you are able to physically damage a molecule. And so this is where you start having some danger from it. All the earlier forms, the visible light, the IR, the FM, the AM, they don't have anywhere near the energy to actually break a molecule. So they can't do any damage to us. Now, that's not to say that you can't be hurt by a lot of IR. Like, if you put something in the microwave, it will get warmer, and the heating can cause damage, but that's not actually the radiation damaging molecules. That's just putting your hand into boiling water. So, when we talk about the danger of radiation, we are talking about if that is able to actually break a molecule on its own. And ultraviolet, X-ray, gamma rays, they are definitely able to do this. Well, the other type of radiation we're going to talk about is nuclear, radioactive elements. So this is the type most of us kind of think about when we think about radiation. For that, I'm going to just talk real quick about where they come from. In the next video, we'll talk about the types. So if you've got a nucleus, you've got a lot of protons, a lot of neutrons. They build up into a mostly spherical seeming material. But these are not necessarily super stable. If you have a lot of positives near each other, they don't want to be near each other. This is why we need neutrons. They hold the protons together. But the bigger and bigger and bigger your nucleus gets, the more difficult this becomes. To the point that eventually you have unstable constructions, where there'll be some kind of empty spaces or ways you could shift things. Nuclear decay comes from turning your nucleus from one unstable set of attachments into a tighter, more stable set. So something might fall in, change position, drag stuff around a little bit. The idea, think like a Jenga tower. So you're playing a game, you got a Jenga tower, there's some random holes, pieces missing in places. Right? That's the worst Jenga tower in all of history. But there you go. So you've got some spots that are missing. If you try to pull one out, you might tip the whole thing over, but a lot of times you might just have like one or two pieces shift, right? And maybe one piece falls off. So what can happen with the nucleus is if it's unstable, parts of the nucleus actually fall out of the nucleus. This is not something that happens in normal chemistry. The nucleus is always the same after you do a chemical reaction, but a nuclear reaction changes that nucleus. And what can come out can be a variety of things. You can have, we'll talk about in detail next video, you can have alpha particles, beta particles, and you can even have gamma particles, which is a bit of a lie. Gamma particles are actually gamma rays. They're not really particles. They're photons. So generally we talk about gamma rays as coming from space, and gamma radiation is coming from nuclear reactions. So we'll discuss that a little bit more in the next video. This is what's actually happening with radioactive decay. You are kicking something out of the nucleus, and that has enormous energy. The energy for a chemical reaction is usually 1/100th or less of a nuclear reaction. So reacting or having a nuclear change, something altering the nucleus, is at minimum 100 times more energetic than normal chemical reactions, which makes it really difficult to ever do. So we don't think about it in terms of a normal chemistry. This only really ever happens in fusion reactions, fission reactions, or the sun. And so we will discuss this in the next video. Thank you for the intro to the ideas of types of radiation, and we're going to dive into what the different types are, which ones are more or less dangerous, and then eventually how we can use them beneficially.